Good day. Welcome to the final video on Chapter 1. This video will be about geometric vectors. Just one video on Chapter 1.8 geometric vectors or arrows. So remember how we defined a line segment. For a line segment, you need 2 points in space, P and Q, 2 different points in space, P and Q. So the line segment S is defined to be the set of points of the form TP plus 1 minus TQ, where T could be 0, T could be 1, or T is bigger than 0, less than 1. So T is sitting in the closed interval from 0 to 1. Now we are going to define a geometric vector, and we denote it by a capital letter, maybe S, with an arrow on top of S, as a directed line segment. So it's a directed line segment in 3D. So it starts somewhere and it ends somewhere. So if the starting point is point Q and the ending point is point P, we say Q is the initial point and P is the terminal point. Alright, so it is basically an arrow in space. So here I have 2 arrows, so geometric vector S and geometric vector T. So I'm putting arrows on top of capital letter S and capital letter T. Now we want to define what does it mean for 2 geometric vectors to be in the same direction. So again, we do this in terms of rays. So if you have 2 geometric vectors S with initial point Q and terminal point P, and geometric vector T with initial point A and terminal point B, we say that if the rays that you can form from those geometric vectors have an angle of 0, then we say that those geometric vectors are in the same direction. So how do you form the rays? So from geometric vector S, you form ray naught. So let's call it ray naught. So we call it ray naught, where you start at the origin plus T, end point minus starting point. So naught plus T, P minus Q, where T is greater or equal to 0. And then you form ray R1. So you form ray R1. So it is all of the vectors of the form 0 plus T, B minus A, where T is greater or equal to 0. So if these 2 rays are identical, then we say that the geometric vector S and T is in the same direction. So if you want to know they're in the same direction, you take the geometric vectors, you form appropriate rays, and if the angle between the rays are 0, then we say S and T is in the same direction. If it turns out that you form these 2 rays and the union of ray naught and ray 1 is a straight line, then we say these geometric vectors are in opposite direction. So all that you need to know is how do you turn a geometric vector into a ray. And so what you do is you turn it into rays starting at the origin. So the direction of geometric vector S is P minus Q, and the direction for geometric vector T is B minus A. Alright, and now we have a definition. So we can say if S and T are geometric vectors, how do you know they're geometric vectors? Capital letters with arrows on top. So if they are in the same or opposite direction, and then we say that they are parallel. So here, it's a tiny typo. Let me fix it quickly. So if they are in the same or opposite direction, then we say they are parallel. Now remember, from high school you learned that a vector has direction and it has magnitude. So how do you define magnitude for geometric vectors? Well, if S is a geometric vector with initial point Q and terminal point P, we define the magnitude of geometric vector S as the norm of terminal point minus initial point, or initial point minus terminal point. So it is the norm of P minus Q. And now we can have a definition. So we say geometric vectors S and T, if they are both non-zero geometric vectors, then we have the following definition. We say geometric vector S is the same as geometric vector T if and only if these 2 geometric vectors have the same direction and the same magnitude. And this now leads to Theorem 1.8.7, is how do you know if 2 geometric vectors are identical? Remember, if S is a geometric vector with initial point Q and terminal point P, and T is a geometric vector with initial point B and terminal point A, then you can prove that geometric vector S is the same as geometric vector T if and only if P minus Q is equal to A minus B. So there's a simple way of knowing if two arrows are identical. Now remember, if you want to prove this theorem, you have two jobs because of the word if and only if. So job 1, you assume the first part. So you assume that the geometric vectors are the same. You work till you manage to show that P minus Q is equal to A minus B. Your second job, you assume the second half of the sentence. So you assume that P minus Q is equal to A minus B. So you work till you manage to show that geometric vector S is identical to geometric vector T. And so from the definition, we know it means that they have the same direction and they have the same magnitude. Another cool theorem. If S is a geometric vector with initial point Q and terminal point P, then you can show there exists exactly one point X in 3D, because here we are playing with 3D geometric vectors, so that geometric vector S is identical to geometric vector T, where T is a geometric vector with initial point, the origin, and terminal point X. Now the consequence of this theorem is the following. If you're given any 3D vector X, we can form a geometric vector with initial point A and terminal point A plus X. And likewise, if geometric vector S starts at point Q and ends at point P, then we can associate that geometric vector S with the 3D vector X as taking the end point minus the starting point. So X is P minus Q. So this means we have a correspondence. Every point can be considered as a geometric vector. And likewise, every geometric vector can be considered as a point. So we can speak simply of a vector in R3 even if we are considering it as a geometric vector, because we have this correspondence between points and geometric vectors. So do take note of that. So this allows us to define and come up with theorem 1.8.11. If P is any non-zero 3D vector and alpha is a non-zero scalar, then if alpha is bigger than 0, then alpha P is a vector in the same direction as P with magnitude alpha times the norm of P. Likewise, if alpha is negative, then alpha P is the vector in the opposite direction, as vector P with magnitude alpha, absolute value of alpha times the norm of P. Alright, because here we can do the correspondence, we can turn every point P, alpha P, as a geometric vector, and if we have it as a geometric vector, then we can use the language and say, what does it mean to be in the same direction and what does it mean to be in opposite direction? Again, turning it into appropriate rays, and if it's in the same direction, then the angle between the appropriate rays is 0, and if it's in opposite direction, the angle between the appropriate rays is pi. So let's quickly do a question that you might get in semester test 1. So the question is, let P, Q, and R and U be the following 3D vectors. So in A, we want to show that R and P have opposite direction. Well, let's have a look at R. So vector R is the vector with coordinates -4, -6, 10. Now have a look at vector P. Well, vector P is a scalar multiple of R. Or we can say R is equal to -2 times 2, 3, -5, which is -2 times vector P. So we see that the scalar is -2 and -2 is negative. So by theorem, it is in opposite direction. So if you get two vectors are scalar multiples of one another and that scalar is negative, then you can say it is in opposite direction. So quickly have a look at B. So look at vector U and P, show that they are in the same direction. Well, let's look at U. U is the vector 8, 12, -20. That is 4 times the vector 2, 3, -5. So it's 4 times P. So now we can say, note, the scalar 4 is positive, so by theorem, it is in the same direction. All right, so very easy calculation. All right, now our model is doing so well that we can even define parallelograms in our model. And it just showcases why the use of geometric vectors is quite useful if you want to consider parallelograms. We are not going to do this in this video, but if you are interested, and please read this is in the textbook. All the work that you need to know about parallelograms is in the textbook. All right, so we can define parallelograms not just in 2D, but we can also define parallelograms in 3D. So the nice way to understand parallelograms is considering geometric vectors. So that is for you to read up. But what I do want to focus on this video, so if you were sleeping, please pay attention now. This is super important. All right? What does some sentences mean? For example, what does a sentence mean when we say vector x is parallel to vector y? Well, it means that vector x is alpha times vector y, where alpha is non-zero. So it means that the one vector is a scalar multiple of the other vector, and that scalar is non-zero. The second sentence, vector x and vector y have the same direction, means vector x equals alpha times vector y, where that scalar is positive. Another meaning that you need to know, vector x and vector y have opposite direction if vector x equals alpha y, where that scalar alpha is negative. More meanings that you should know. The angle between vector x and vector y is the angle between rays tx, where t is greater to 0, and ty, where t is greater to 0. So what you do here is you form two rays. Any origin, we just pick the origin to be of the rays as the zero vector, and the direction of ray naught is x, and the direction of the other ray is y. All right. So this allows us to define the angle between vectors by forming appropriate rays, and if the angle between the rays is a certain value, that is the angle between the vectors. And this leads to more definitions or meanings. So we say vector x is perpendicular to vector y if the dot product between x and y is 0. So it's quite easy to check if two vectors are perpendicular. The dot product is 0. Likewise, vector x is parallel to line L. So here we're saying a vector is parallel to a line, and let's say the line is of the form p plus tq, where t is any real number. If and only if vector x is a scalar multiple of vector q, the direction of the line, and alpha is non-zero. Again, that scalar must be non-zero. We also say that vector x is perpendicular to the line L. Oh, let's use the same form, p plus tq, where t is a real number, if and only if x dot q is equal to the value 0. And two more that you need to know. Vector x is parallel to plane p. All right, so vector x, so this is vector x, it is parallel to plane p, means that the normal, so a normal of the plane, so let's call it n, is perpendicular to n. So sorry, my picture that I've just sketched, I wanted that the following, that vector x is parallel to plane p if and only if vector x is perpendicular to a normal n. And then the last one that you need to know is the following, that if you have a vector x and you have a plane p, then you can say vector x is perpendicular to plane p with normal n if the vector x is parallel to a normal of the plane. All right, so please summarize this neatly for you in a table so that you know what these fragments mean. So if it appears in a problem or in a semester test or in the exam, that you know what is going on here. All right, and it's sometimes good to draw pictures. So I want to finish this video by looking at a type of question you can get in semester test 1. So let's read the question. Find all real values alpha so that the vector x, it's some 3D vector, is parallel to the plane with Cartesian equation 2x minus alpha y plus 3z equal to 1. So you can see this is a plane because it's the form ax plus by plus cz equal to d. Alright, so let's quickly draw. So you might not get any marks for drawing, but it gives you an idea of where to start. So you have some flat surface, some plane P, and then you have a vector x. So you have a vector x, and you want the vector x to be parallel to the plane. So now this meaning comes into play. Number 8, a vector is parallel to the plane if vector x is perpendicular to the normal. So when you solve this, you need to know a normal. Alright? So a normal to the plane P, that's very easy to work out. You take the coefficient of x, which is 2. You take the coefficient of y, yep, that's minus alpha, and you take the coefficient of z, which is 3. So you need to have the right vector. So now we can say that x is parallel to P if and only if x is perpendicular. So let's write down the long word, perpendicular to n. So we want those two vectors to be perpendicular. So again, what does it mean for two vectors to be perpendicular? This is now number 5 making an appearance. So number 5 says that two vectors are perpendicular if and only if the dot product is the value 0. So now that bit of knowledge comes into play. So this happens if and only if x dot n is equal to 0. Alright, and now we can do the mathematics. So x dot n, we want this to be 0. So vector x is the vector with components 1, 2 minus alpha, comma, minus 1. N is the vector 2 minus alpha 3, that's equal to 0. And by now you must be excellent at working out dot products. So you multiply the first components, that is 2. You multiply the second component, so that becomes minus 2 alpha plus alpha squared. And you multiply the third component, minus 3 is equal to 0. And now let's quickly simplify. This simplifies to alpha squared minus 2 alpha minus 1 is equal to 0. It doesn't appear to factorize, so I use the quadratic formula. So I get alpha is equal to minus b plus minus the square root of b squared minus 4ac divided by 2a. So it simplifies to 1 plus minus square root 2. And that, ladies and gentlemen, is the answer to this question. So you can see you need to know what it means for a vector to be parallel to a plane. I hope you enjoyed this video, and this is the end of chapter 1 about vectors. So I hope you've learned a lot, and please make sure that you do a lot of exercises in the textbook to make sure that you are comfortable with playing with vectors, especially in 3D. Have a good day. Bye.